Hello, and welcome to our video providing an overview of our WASPAA paper, which is entitled Rendering of Source Spread for Arbitrary Playback Setups Based on Spatial Covariance Matching. In this work, we propose a general algorithm which can take a mono signal as input and reproduce it over a target playback system with a certain degree of source spread. That is to say that the sources have some perceivable physical extent rather than being point sources. And the aim is for the spread sound source to be diffuse, or rather mutually incoherent across its full extent. However, as one might already assume, this diffuse source rendering is going to require the use of signal decorrelators. So the secondary goal of the algorithm is to also preserve the original signal quality as much as possible. The starting point for the proposed algorithm is to first measure, model, or simulate the directional responses for the target playback system for many directions. For example, these can either be head-related transfer functions, microphone array transfer functions, or they could be spherical harmonic vectors or amplitude panning gain vectors. In all cases, these directional responses can be stacked into one matrix like so. And one common and simple way to generate a spread sound source over the target playback system is through this coherent spreading approach. Here we create multiple identical copies of the input mono signal and convolve them with each directional response that fall within the spreading area, and then we simply sum them up. Note that this summing is over the entire intended spreading area, which can be arbitrarily defined. For instance, this could be for the whole sphere, a circular area on the surface of the sphere, or the area can be more complex and informed by a game audio engine or maybe even drawn by the user. Some examples of this coherent spreading approach include MDAP, which is based on computing multiple amplitude panning gains, vectors, which correspond to directions that surround the central source direction. Then, of course, there is ampersonic panning, which inherently encodes sound sources with coherent spreading. And this spreading width is dependent on the spherical harmonic order and then ultimately on the playback system. And the benefit of coherent spreading is mainly that it's easy to implement, and it can sound pretty reasonable if the source spread is narrow. However, as the source spreading area grows larger, you'll find that summing localization actually starts to perceptually collapse the sound source into narrower sound events. You'll also start to experience signal colorations, which are commonly experienced with lower order ambisonics reproduction. One modification to this coherent spreading is to take the input mono signal, divide it into frequency bands, and then assign each band to a different direction within the spreading area. So the formula is much the same as it was before, except the spreading directions change across frequency. This therefore bypasses many of the problems that you may experience with the previous purely coherent spreading. And it's also quite easy to implement, and listening tests have shown that this source spreading can be perceptually quite convincing. However, the problems with the approach have to do with the varying performance depending on the spectra of the input signal. In the most extreme example, if you have just a sine tone input, then there would be no spreading, and you would instead get a directional shift of the sound source. So the frequency resolution plays a major role in determining how well this approach works, and it also depends on how you assign these frequency-dependent directions within the spreading area. Which now brings me to the source spreading model used by our proposed method. So we intend to target an incoherent source spreading, which is to say that we want the sound source to be diffuse across the full extent of the spreading area. So the cross correlations between the signals within the spreading area should be zero, whereas the autocorrelations should correspond to the source power. And the simplest way to realize the target spreading model would be to replicate the input signal as many times as there are directional responses within the spreading area, and decorrelate them all prior to applying the directional responses. So we are now effectively distributing incoherent copies of the input signal rather than coherent copies of the input signal as we were before. So we are directly implementing the target sound field model. And if decorrelation was perfect, then this approach would also be perfect, and we wouldn't have to go further than this. However, high-quality decorrelation is challenging in practice, and any signal quality degradations that may occur will be aggregated across this summation. So the larger the spreading area, the more directional responses will fall within the spreading area, and the worse the output signal quality may become. This is why in the literature you'll find that those who have researched incoherent source spreading have suggested using far fewer directions within the spreading area to mitigate this problem. However, these methods tend to be rather ad hoc and intended only for certain playback setups, so are not easy to generalize to arbitrary setups. And this brings me to the idea of using spatial covariance matching for the task of source spreading. This is where, instead of thinking about how we can spatialize incoherent copies of the source signal, we try to think what are the correct interchannel dependencies that would correspond to the desired diffuse sound source spreading. Since after all, we know that the output signal powers and the output signal correlations should give us all the information we need to represent an incoherently spread sound source. In other words, we would like the spatial covariance matrix of the output signals to exhibit this target spatial covariance matrix. And we can outline the problem as finding the appropriate mixing matrix to apply to incoherent copies of the input signal so that we may produce output signals that conform to this target spatial covariance matrix. And it's important to note that the maximum number of decorrelators we need to reproduce a full incoherent field will be the same as the number of channels in our playback system. So the number of decorrelators that are required will always be clear, so the approach has already become more general than the previously mentioned ad hoc alternatives. And one possible solution is what we'll now refer to as the unconstrained solution, which is based on the eigenvalue decomposition of the target spatial covariance matrix. And on the surface, it looks like this simple solution is all we need. However, while we are technically directly conforming to the target model, and the number of decorrelators that are required for arbitrary setups has become more clear, the main issue is that there are an infinite number of solutions to this problem, since this equation holds true for any unitary matrix Q. And just because you are able to obtain signals that have the interchannel dependencies corresponding to the target model, doesn't mean that these rendered signals will actually sound good. Which is why in our paper we propose using the optimized covariance domain framework proposed by Wilkemo et al., which effectively exploits these additional degrees of freedom in order to optimize the solution to preserve signal quality. And it tries to reduce the amount of decorrelated signal energy in the output signals. So what we do is to first pan the input signal to the center of the intended spreading area. The optimized framework then computes matrix M, which linearly maps these signals to the output channels, while trying to ensure that these output signals reflect the target spatial covariance matrix as much as possible. And in some cases, this matrix might be enough to fulfill the target model. However, if it is not, then we use this additional matrix to map a decorrelated copy of the center pan signals to the output channels, thus fulfilling the remaining target interchannel dependencies. And this now brings me on to the evaluation, which we did in the context of binaural playback. Therefore, we used a dense grid of head-related transfer functions as our directional functions. And the reason we chose binaural rendering is because this is perhaps one of the more likely playback formats in practice. It is also quite easy to do a meaningful objective evaluation since the interchannel differences of the output binaural signals relate directly to the perceptual interoral cues. So these would be the interoral level differences, the interoral coherence, and the binaural coloration. And the reason we chose to do an objective evaluation was also because we were under a lockdown at the time due to the pandemic. So we created a number of synthetic renderings with various different source directions and degrees of circular spread. And this first part of the evaluation was based on using white noise as the input stimuli. The rendering approaches that we tested were the unconstrained spatial covariance matching approach and the proposed constrained alternative approach. We then also had a reference case based on convolving uncorrelated white noise signals with HRTFs within the spreading area. So this would be the perfect incoherent spreading condition. And as an additional frame of reference, we also included a coherent spreading option as a baseline case. And here is an example of the objective metrics plotted over frequency. In this particular example, a source was panned 45 degrees to the left of the listener with 60 degrees of circular spread. And essentially, we're interested in how close does each rendering method get to the reference case. And this was then rerun for many different source directions and degrees of spreading, and thus made up this part of the objective evaluation. And here are the results. So these are the root mean square errors and standard deviations, which were computed with respect to the reference case. And these are based on all 841 directions of the employed HRTF set, and also averaged over frequency. As you can see, when the source spreading is 0, all three methods revert back to point source panning, so the error is also 0. As the spreading increases, so does the error, but the two spatial covariance matching approaches always produce lower errors than the popular coherent spreading baseline approach. However, while the perceptual metrics allow us to infer that the covariance matching approaches are conforming to the target model better than the coherent spreading baseline, it does not give us any indication of the output signal quality. Therefore, we also computed this signal distortion metric in the time domain. And this was based on a number of different input stimuli, which were not white noise. And here are the results for this signal distortion evaluation. Note that a higher value infers worse quality of the output signals. So although the unconstrained approach produced low errors in the perceptual metrics evaluation, it is indicated here that this is to the detriment of the signal quality. And to provide additional insights into the perceived performance of these spreading approaches, we invite you to listen to pre-rendered audio examples, which may be found on the companion website for this paper. We also developed an open source implementation of the same spreading approaches, which were realized as a VST audio plugin and may be used to render some of your own source material in real time. Note that by default, the plugin assumes a binaural output and therefore loads a default HRTF set. However, you may also load, for example, your own personalized HRTFs or even microphone array impulse responses via the software format. And that brings us to the end of the talk. Thank you very much for listening.